So imagine a tightrope walker. But they aren't just walking a straight line. They are walking this razor-thin cable while entirely blindfolded, suspended over a canyon.
Right, that is exactly what it feels like.
Yeah, and in radiation oncology, when you prescribe a massive dose of radiation to eradicate a tumor, you're often prescribing at the absolute bleeding edge of what the surrounding normal, healthy organs can actually survive.
You really are. The margin is just, well, it's virtually zero.
Exactly. So if you're a medical student prepping for your boards or a young professional stepping into the clinic, or honestly just a dedicated self-learner trying to understand the incredible physics of cancer treatment, you know the stakes here.
Oh, absolutely.
Today, we're taking on a comprehensive, jargon-free deep dive into the textbook Practical Radiation Oncology Physics by Dieterich, Ford, Pavord, and Zeng. Our mission is to bridge that incredibly intimidating gap between, theoretical physics on a whiteboard and actual life-or-death clinical safety.
And it is such a critical gap to cross,
Yeah.
right? Because you are managing this invisible destructive force. I mean, if you underdose the target, the tumor survives, mutates, and grows.
Right.
But if you overdose even slightly,
Yeah.
you risk catastrophic complications. We're talking about destroying a patient's spinal cord, paralyzing them, or destroying their bowel.
Which is terrifying.
It is. So the central question we have to answer today is, how do modern clinical teams wield this invisible scalpel without making a fatal mistake?
Yeah, and before you can even think about treating a living, breathing patient, you have to be able to measure that invisible force first. You absolutely cannot safely prescribe what you can't perfectly measure.
Exactly. We just can't.
So let's start at the very foundation, which is reference dosimetry. The textbook spends a lot of time on these international codes of practice, AAPM TG51 in the US and IAEA TRS 398 internationally.
Yeah, they sound like confusing tax forms, don't they?
They really do. But they're essentially the universal rule books for calibrating a linear accelerator, right?
They are the absolute bedrock of everything else we do. They dictate exactly how we determine the absolute dose of radiation firing out of a machine. And the primary tool we use to do this is an ion chamber.
Okay, so to visualize an ion chamber, I just picture this small, hollow thimble made of plastic or graphite, and it's just filled with normal air.
Yep, that's exactly it. When you blast it with a radiation beam, the radiation physically rips electrons off the air molecules inside that cavity.
Wow.
Yeah, it creates these free-floating electrical charged ions. Then we apply a voltage to the chamber to collect those charges, measure the tiny electrical current, and, well, that gives us a reading.
Okay, let's unpack this a bit, because you get a raw electrical reading from the air inside the thimble. But, humans aren't made of air. We're mostly water.
Right, which is a huge distinction.
So you have to mathematically convert that air reading into what they call absorbed dose to water. And you can't just plug the raw number into a calculator and call it a day. You have to apply a very strict series of correction factors.
You really do.
Yeah.
Because air is highly sensitive to its environment. Let's just look at temperature and pressure for a second.
Okay.
If the room is a few degrees warmer than standard, the air inside that tiny thimble expands. Some of the air molecules actually get pushed out of the chamber's sensitive volume.
Oh, I see.
Yeah, so if there are fewer molecules in the chamber, there are fewer molecules for the radiation to hit, which means you collect less electrical charge. Your meter will basically tell you the radiation beam is weak, even if the beam is perfectly fine.
Wait, so if a young physicist forgets to check the room's thermometer, they might accidentally turn up the radiation output to compensate for a quote-unquote weak beam?
Exactly.
And suddenly the patient's getting overdosed just because, the AC was broken that morning.
That is the exact mechanism of failure we have to avoid. And temperature isn't the only variable here. The text goes deep into ion recombination, too.
Right, I remember that part.
Remember how we said the radiation splits the air molecules into positive ions and negative electrons, and we use a voltage to sweep them up? Well, if we don't sweep them up fast enough, they actually physically bump back into each other and recombine into neutral air molecules before they ever reach our measuring wire.
Oh, wow. So you just lose the signal entirely.
You do. So we have to calculate a recombination correction factor to account for the charges we lost. All of these obsessive corrections, temperature, pressure, recombination, polarity, they're applied to achieve one massive clinical goal.
Which is keeping the combined error in your total dose delivery to 5% or less, right?
5%. That is the magic number to keep patients safe.
It's crazy that it's so tight. But measuring the beam in a water tank once a year, like reference dosimetry, that's only the start. The text also covers relative dosimetry, which is mapping out the 3D shape of the beam so the software knows how to model it.
Yeah, and in vivo dosimetry, where we tape detectors directly onto the patient's skin to catch errors in real time.
Right. But here is where it gets incredibly dangerous if you don't understand the physical limits of your tools. Using a standard-sized ion chamber to measure a tiny millimeter-wide stereotactic radiation beam. Well, I like to think of it like trying to weigh a single grain of salt using an industrial truck scale.
That's a great analogy.
Hmm.
What's fascinating here is the physical phenomenon driving that. It's called volume averaging.
Volume averaging, right?
Yeah. If your detector is, say, 6 millimeters wide, but you are trying to measure a radiation beam that is only 4 millimeters wide, part of your detector is sitting in the intense radiation, but the outer edges of your detector are just sitting in dead air.
Oh, I get it. And the detector doesn't know the difference.
Exactly. It just averages everything together.
So the detector blends the high dose with the zero dose, spits out an average, and basically tells you, hey, this beam is really weak.
Yes, and if you trust that detector without questioning the physics behind it, you cause a catastrophe.
Yeah, and the textbook highlights a tragic cautionary tale that every medical student and physicist must know. In Springfield, Missouri, over a 5-year period between 2004 and 2009, a clinic was using standard-sized detectors to measure the output of a very small stereotactic radiosurgery cone.
Which was specifically designed to treat tiny brain tumors.
Right. And because of volume averaging, the detector drastically underreported the radiation dose. The clinic believed their machine was underperforming, so to compensate, they went into the software and cranked up the machine's output.
It's just devastating.
It really is. Consequently, 76 patients received a massive 50% overdose to their brains.
76 people, it's absolutely heartbreaking. And especially because it wasn't a mechanical glitch, you know? The machine was doing exactly what it was told to do.
It completely illustrates why we can't just blindly trust a digital readout. If you're listening to this on your commute and you take away one thing, let it be that you have to know your equipment's blind spots.
It really underscores why independent secondary checks are non-negotiable. This is even more critical today as clinics adopt non-standard beams.
Like the CyberKnife or Gamma Knife.
Exactly. Those machines don't produce flat, predictable dose profiles. They have these inherent steep gradients. You need highly specialized microdetectors and very complex correction factors to measure them safely.
Right, you must have an accredited, independent lab, verify your local calibrations annually.
Without a doubt.
But, measuring the radiation perfectly is only half the battle. Once you trust your ruler, how do you handle the scalpel? A perfect dose calculation means absolutely nothing if you miss the tumor.
So true.
The text dedicates major sections to the modalities of delivery: protons, brachytherapy, and moving targets. Let's start with protons because this feels like a massive leap in how we actually deposit energy into the body.
It is a fundamental shift in physics.
Huh.
With standard photon radiotherapy high-energy X-rays, the beam enters the body, starts depositing energy immediately, hits the tumor, and then just continues to punch right through the patient.
Depositing radiation into healthy tissue as it exits the other side.
Right. But protons are different. They are heavy, charged particles. You accelerate them, fire them into the tissue, and they travel relatively quietly until they reach a very specific depth.
And then boom.
Yeah, they dump almost all of their destructive energy at once in a phenomenon known as the Bragg peak. And then they stop completely. There is zero exit dose.
Here's where it gets really interesting for me. I picture a proton beam as like a microscopic depth charge. You drop it into the ocean, it sinks down without doing any damage, and it is perfectly timed to explode at exactly 40 feet deep.
That's a really good way to visualize it.
Yeah, obliterating the submarine but leaving the fish at 41 feet totally untouched. But wait, I'm kind of stuck on this. A tumor isn't a two-dimensional dot, right?
Right.
It has 3D volume.
Right, it does.
So if a proton explodes at one specific millimeter, how do you blow up a whole tumor without just firing a million depth charges and accidentally chewing up the healthy tissue anyway?
Well, that is the exact engineering hurdle physicists had to solve.
Huh.
One native Bragg peak is way too narrow to treat a whole tumor. So we create what's called a spread-out Bragg peak, or SOBP.
Okay, SOBP. How does that work?
We essentially fire a sequence of proton beams at slightly different energies. Lower energy protons stop shallower, while higher energy protons go deeper.
Oh, I see.
Yeah, so by stacking these sequential explosions on top of each other, we stretch that sharp peak out into a wide plateau of dose that covers the entire depth of the tumor.
Okay, that makes sense. You just paint the whole volume layer by layer.
Yes, but we also have to account for the biology, not just the physics. Protons cause a different type of damage than X-rays. We measure this using relative biological effectiveness, or RBE.
RBE, right.
The clinical standard is that protons have an RBE of 1.1. This basically means that 1 gray of physical proton radiation causes the same biological devastation to a cell as 1.1 gray of photon radiation.
Wow.
And if you look at the bleeding edge of the field, heavy ions like carbon have an even higher RBE. This is due to something called linear energy transfer, or LET.
Linear energy transfer, so how does that change things?
Well, heavy ions just plow through the DNA like a bulldozer, causing these really complex, clustered DNA double-strand breaks that the cancer cells simply cannot repair.
Man, it is incredible technology. But sometimes, instead of shooting particles from a machine outside the body, we place the radioactive material directly inside the patient.
Right, which brings us to brachytherapy.
Yeah, the text sharply contrasts high dose rate, or HDR, with low dose rate, LDR.
The clinical applications are very different, though the safety principles definitely align. HDR usually utilizes an iridium-192 source. It is incredibly radioactive.
Like fiercely radioactive.
Exactly. The source is welded to the end of a wire, and a machine temporarily drives it through catheters directly into the tumor, say a breast or cervical tumor. It leaves it there for a few minutes to deliver a massive dose, and then pulls it back into the safe.
Okay, and LDR is different.
LDR, on the other hand, often utilizes iodine-125. These are tiny, permanent radioactive seeds. A surgeon permanently implants dozens of them directly into an organ, like a prostate gland.
And they just slowly release their energy over several months as the patient goes about their normal life.
Exactly.
And the physics requirement for both is absolute precision in calibration. You use an air-filled well chamber to measure them. I know the goal is to find the sweet spot in the chamber.
Yeah, you are basically looking for the position of maximum reading. When calibrating an HDR source, the physicist literally steps the radioactive source through the weld chamber millimeter by millimeter.
Oh, wow.
They record the electrical current at each stop until they find the peak reading. The golden rule in the clinic is that your physical measurement must match the manufacturer's shipping certificate within 3%.
3%, that's strict.
It is. If it's off by more than 5%, you halt everything. You do not treat the patient, you just send it back.
But wait, if you're dealing with LDR, those permanent iodine seeds, they arrive at the clinic totally sterilized and sealed in packaging, ready for the operating room. How do you practically drop them into a well chamber to calibrate them without breaking sterility?
It's a great practical question, because you obviously cannot implant a contaminated seed into a human being. The text offers some really practical clinical workarounds.
Like what?
Often, clinics will intentionally order extra seeds from the exact same manufacturing batch. These extra seeds are specifically designated for assaying. You test the extras in the weld chamber to verify the entire batch's strength, and then you just dispose of them.
Oh, that's smart.
Yeah. Alternatively, there are specialized calibration jigs. These are sterile plastic inserts that allow you to drop the sealed seeds into the detector while maintaining their sterile envelope.
I see.
The rule is you must independently assay a certain percentage of the shipment, typically 10% of the seeds, or 10 seeds, whichever is greater, before the patient ever goes under anesthesia.
You literally build the cost of safety right into your equipment orders. Now, whether you're using protons or placing radioactive seeds or using standard external X-rays, the patient isn't a statue.
Definitely not. They breathe. Their heart beats.
Right. Their internal organs are constantly shifting.
Which brings us to image-guided radiotherapy, or IGRT. Consider a prostate gland. It is not anchored in a fixed anatomical position. It floats in the pelvis, and its position changes drastically from day to day or even minute to minute.
Based entirely on how full the patient's bladder or rectum happens to be, right?
Exactly.
So if you map the tumor on Monday, but the patient drank a lot of coffee on Tuesday, the bladder expands, pushes the prostate 2 centimeters to the left, and suddenly your perfectly aimed beam is blasting healthy rectal tissue instead of the cancer.
Precisely the danger.
Yeah.
So we use IGRT to track it dynamically. We might use daily ultrasound sweeps or on treatment CT scans built right into the linear accelerator.
That's cool.
We can even implant radio frequency beacons into the tumor that broadcasts its location in real time. If we connect this to the bigger picture, the common denominator across all these complex modalities is stringent geometric and temporal accuracy.
You have to know exactly where the beam is in 3D space, and where the tumor is in the patient's body.
And you must verify that those two targets perfectly align at the exact millisecond the beam turns on.
Which naturally drives us to a massive thematic transition in the text. With delivery systems becoming this wildly complex, intensity-modulated beams, real-time tumor tracking, robotic arms, having a physicist just check the machine's calibration with a water tank is completely insufficient.
It really is.
We've officially entered the era where we must analyze the human-machine interface.
We are talking about the paradigm shift towards systems thinking. Historically, the field was hyper-focused on prescriptive, machine-level quality assurance.
Yeah.
Like, does the laser align? Does the jaw open to the right width?
Right, the mechanical stuff.
Exactly.
Yeah.
But modern quality management recognizes that the machine is only one tiny node in a vast, highly complex clinical workflow involving dozens of humans and software handoffs.
And this shift wasn't just some academic theory. It was born out of terrible tragedy. The text highlights several watershed accidents that completely galvanized the medical physics industry, most notably the tragic death of Scott Jerome Parks.
Yes.
For those who aren't familiar, he was a patient receiving treatment for head and neck cancer in New York, and he received a massive, fatal radiation overdose.
And what is so vital to understand about the Scott Jerome Parks tragedy is that the linear accelerator did not break. The machine delivered exactly the amount of radiation the computer told it to deliver.
It was a human-computer interface issue, wasn't it?
Yes. The failure was a cascade of workflow breakdowns. The treatment plan was imported into the machine incorrectly. Because of a software interface glitch, the heavy lead leaves the multi-leaf collimator that shapes the beam to protect healthy tissue. They remain completely open instead of conforming to the tumor.
And the therapist running the machine actually saw error messages on the screen, right? But they were so used to seeing generic error codes pop up during perfectly normal treatments that they just hit Mentor to clear the screen and turn the beam on.
Exactly. They were desensitized by poor software design. And there was a breakdown in communication. The physicist wasn't properly consulted when the software struggled to save the file.
So the system failed them.
It was a classic systems failure. The system was designed in a way that allowed humans to make a totally foreseeable mistake, and it lacked the independent safety nets to catch that mistake before the beam turned on.
So what does this all mean for a young physicist or a physician setting up a modern clinic? The text outlines the pillars of modern quality management, like peer review, such as chart rounds where physicians critically debate each other's contours.
And physics initial plan review, where a second physicist checks the math, plus checklists and incident learning.
But let me ask you about checklists. We hear a lot about checklist fatigue in medicine. If you give a therapist a checklist with 40 boxes to tick before every patient, they're just going to blindly scribble checks down the page.
Right. It becomes white noise.
Yeah. That seems like it could be just as dangerous as having no checklist at all.
It's a massive vulnerability. A poorly designed bureaucratic checklist just creates white noise, like you said. But true systems thinking teaches us that human error is almost never the root cause of an accident.
That's a big shift in mindset.
It is. If a therapist blindly ticks a box and hurts a patient, the root cause isn't that the therapist is lazy. The root cause is a systemic flaw that created an environment of fatigue, understaffing, or poor interface design.
So how do we fix the system before a patient actually gets hurt, instead of waiting for a crash to figure out what broke?
The text details proactive tools, specifically FMEA failure mode and effects analysis. You don't wait for an accident. You sit down with your entire team, doctors, physicists, therapists, dosimetrists, and you map out every single step of your clinical process.
Okay, so breaking it all down.
Yeah. Let's say step 14 is transferring the plan over the hospital network to the machine. You actively brainstorm. What happens if the network drops a packet? What happens if the file gets corrupted?
And then you score the risk, right?
Exactly. You assign a risk priority number based on three things: how severe the failure would be, how frequently it might happen, and how likely your current systems are to catch it. You multiply those numbers together.
And the steps with the high scores are where you build your safety nets. You force independent second checks on the most dangerous steps.
Precisely.
And when things inevitably do go wrong, because humans are involved, you use RCA root cause analysis to dig backward past the human error to find the latent system flaw.
And to facilitate this on a national scale, the industry created ROILS, the Radiation Oncology Incident Learning System. It is a federally protected patient safety organization in the U.S.
Which is huge for transparency.
It really is. Clinics can report their near misses, the times a patient almost got hurt, but someone caught it into a national database without any fear of legal discovery or lawsuits.
Oh, that's brilliant.
Yeah, it treats safety as a collaborative, transparent science rather than a liability to be swept under the rug. It allows a clinic in Ohio to learn from a software glitch that happened in a clinic in Texas, preventing a fatal accident.
It's incredible. So we've established the foundation of measurement, the mechanics of delivery, and the systems thinking required to keep it all safe. But what happens when the clinical situation forces a team to operate at the absolute extreme edges of standard practice?
That's where things get really intense.
Yeah, the text has a fascinating section on high-risk edge cases. Let's talk about intraoperative radiotherapy, or IRD.
IRD is an intense scenario where the standard rulebook has to be carefully adapted. You are delivering a single, massive, sterilizing dose of radiation directly into an open tumor bed while the patient is literally open on the surgical table.
It sounds like science fiction. Why not just wait until the patient heals from surgery and treat them normally?
Well, imagine a surgeon is trying to remove a tumor in the abdomen, but the tumor is wrapped microscopically around a vital blood vessel or a major nerve.
Okay.
The surgeon cannot physically cut it all out without destroying the nerve. With IRT, the surgeon physically moves the sensitive, healthy organs out of the radiation field. They use retractors to push the bowel away.
Oh, wow.
Then the radiation oncologist brings in a specialized mobile linear accelerator and delivers a massive dose of electrons directly to the remaining microscopic disease. The physical displacement of the healthy organs is what makes it safe.
That is wild. Another extreme scenario the text details is total body irradiation, or TBI.
Right. TBI is generally used as a conditioning regimen for a bone marrow transplant in leukemia patients. We are intentionally irradiating the patient's entire body from head to toe to suppress their immune system so they don't reject the donor marrow.
And to eradicate circulating leukemia cells.
Exactly. From a physics perspective, it requires entirely specialized tools. For example, we use beam spoilers.
Let's break that down. Because normally, a high-energy X-ray beam penetrates deep below the skin before it unleashes its maximum dose. We call that the skin-sparing effect, which is great for treating deep tumors without burning the patient's skin.
Right, but in TBI for leukemia, the skin is heavily vascularized. Leukemia cells hide in the capillary beds of the skin. If we let the radiation penetrate deep before building up, those superficial cancer cells will survive.
So you have to spoil the beam.
Yes. You place a beam spoiler, literally a massive physical screen, often a thick sheet of plexiglass between the machine and the patient. The high-energy beam hits the plexiglass, scatters the electrons early, and deposits its maximum destructive energy immediately upon touching the patient's skin.
And because a human body is not a perfectly uniform cylinder, like your neck is thinner than your chest is thicker than your ankles, you have to use custom tissue compensators so the thinner parts of the body don't get totally overdosed.
Exactly. We also have to machine custom heavy lead blocks to protect the lungs. Without lung blocks, the massive whole-body dose would cause fatal radiation pneumonitis. The complexity of the physics calculations required for TBI is just immense.
Which brings us to perhaps the most sensitive and ethically complex edge case in the text: pregnant patients. The textbook notes a critical safety threshold of 10 centigrade of fetal dose, particularly in the first 15 weeks of gestation.
Fetal tissue is rapidly dividing, making it incredibly sensitive to radiation damage.
Yeah, and the text strongly emphasizes assessing pregnancy status, like running mandatory HCG tests before the patient ever gets near the CT simulator. But I have an empathetic, practical question here.
Sure.
If a pregnant patient has a highly aggressive, life-threatening cancer, say, a brain tumor, and must be treated immediately to save her life, how does the team possibly balance the mother's survival against that 10 centigrade at a limit?
It is one of the most stressful scenarios in the field, and it highlights the ultimate value of the medical physicist. In this scenario, the physicist is not just running numbers in a back room. They become a critical clinical consultant.
Right.
It requires an intensive, multidisciplinary approach. The radiation oncologist, the maternal-fetal medicine obstetrician, and the physicist sitting down at a table together.
Because you can't just point the beam at her head and assume the fetus in her abdomen is perfectly safe. Radiation bounces.
Exactly right. The physicist's job is to meticulously model the out-of-field scatter. Radiation scatters inside the patient's body, and leakage radiation physically penetrates through the heavy shielding in the head of the linear accelerator.
So they have to calculate all of that stray dose.
Yes, they calculate exactly how much of that stray dose will travel down to the fetus. Then they design custom external shielding. I have seen physicists literally build physical bridges out of heavy lead blocks over the pregnant patient's abdomen on the treatment table.
That is amazing.
They measure the scatter, adjust the lead, and drive that fetal dose as low as physically achievable, allowing the mother to receive her life-saving treatment while protecting the pregnancy.
It really highlights the profound responsibility of the role. You aren't just calibrating equipment, you are actively engineering solutions to save two lives at once.
It's an incredible field.
All right, as promised at the top of the show for our medical learners and students prepping for exams, it is time for a quick mental exercise to lock in the absolute most critical concepts we've covered today.
Sounds good.
Think back to our discussion on reference dosimetry and the Springfield incident. Here is the scenario. You are performing a daily morning QA check on a non-standard small stereotactic cone. You notice your ion chamber reading differs by a massive 6% from your established baseline.
Okay, a 6% deviation.
Based on what we discussed about detector size and the underlying mechanics of volume averaging, what is your immediate next step and what specific equipment check must you perform?
I will give you a second to think through the mechanism. The clinical answer is, your immediate next step is to halt all patient treatments. You absolutely do not adjust the machine output to artificially compensate for the weak reading.
Right, because that's what caused the Springfield accident.
Exactly. The specific equipment check you must perform is to verify if your ion chamber's physical volume is larger than the small beam size. If it is, you are experiencing volume averaging. You must then find an independent, appropriately sized microdosimeter and verify the physical dose before a single patient enters the room.
If you got that right, you are well on your way to understanding the true core of clinical safety. Before we wrap up, I want to ask you for a final provocative thought. We've covered a massive amount of ground today, from the rigid math of TG51 to the psychological nuances of systems thinking and FMEA.
We really have.
Looking forward, where is the field of medical physics heading?
Well, I want you to ponder this. We're standing at a precipice. As artificial intelligence begins to rapidly automate treatment planning, contouring tumors, and as machine learning algorithms take over routine QA tasks, the fundamental role of the medical physicist is going to shift radically.
Oh, that makes sense.
In the near future, you won't just be calibrating the mechanical parts of a linear accelerator. You'll be actively calibrating the AI. You will be auditing black box algorithms to ensure they don't hallucinate a fatal dose.
Wow.
And that makes the systems thinking we discussed today not just a regulatory safety protocol, but the absolute most critical clinical skill of the 21st century.
Calibrating the AI, that is a wild and very real frontier. It means understanding the why behind the physics is more important than ever because the computer will do the what for you. We hope you take these safety paradigms, the deep mechanical understanding of your tools, the systems thinking that assumes humans will fail, and the proactive FMEA analysis and actively apply them to your own clinical rotations or your own understanding of the field. Remember that tightrope walk. You are operating right at the razor's edge of what human tissue can tolerate. Respect the invisible force, trust your secondary checks, and never, ever stop questioning the system. Thanks for joining us on this deep dive.